When we look at the percentage of water distribution worldwide, we see that the ocean makes up approximately 70% of the Earth's surface and accounts for 96% of the water on the planet. With 783 million people lacking access to clean water and more areas facing severe droughts, seawater desalination is becoming more prevalent in many parts of the world. The composition of seawater is made up from mostly sodium and chloride, so the potential for inorganic scale is relatively low. However, there is a higher potential for organic fouling. A typical membrane desalination plant includes intake, pretreatment, seawater reverse osmosis process, and post-treatment. Each of these elements are crucial. However, the membrane process is the heart of desalination. The seawater RO process is often operated at recovery rates between 35 to 60%, with pressures ranging between 600 and 1200 psi. Due to the high pressure requirements, it is important to maintain low pressures. Intake selection is extremely important when looking at membrane fouling potential. Often, runoff containing nutrients such as nitrogen and phosphorus can trigger algae blooms. An open intake may have a higher potential for organic fouling and algae blooms. A subsurface intake provides additional feed water treatment so the impact of algae blooms may be minimized. When dealing with hazardous algae blooms, it is important to understand how this impacts membrane performance and fouling deposition on membranes. When algae multiply and die, transparent exopolymer particles, or TP, is released. These particles can adhere to the membrane surface, creating a polysaccharide layer that acts as a food source for bacteria to attach and reproduce. The biofilm grows, becomes thicker, and encapsulates sessile bacteria, enabling the biofilm to protect itself from biocide addition. Larger microorganisms, such as nematodes, diatoms, and amoeba, may develop above the mature biofilm, further protecting the initial layer. A seawater facility experienced high feed and differential pressures due to severe biofouling. Several elements were collected, autopsied, and full element cleaning studies were conducted. Here we have the unclean membrane surface. The membrane is covered in a tan gelatinous material that was determined to be organic fouling. To look at the spatial distribution of the foulant on the membrane surface, we use chromatic elemental imaging. From the imaging, we see the dark blue representing carbon, which in this case represents the organic material. The crack in the imaging reveals the membrane layer. This imaging indicates a significant organic fouling layer. Through testing, we identified that a targeted high pH cleaner, Avista 192, combined with RoClean P303, a low pH cleaner, resulted in a virtually foulant-free membrane surface and demonstrated a 44% drop in pressure. In many cases, membranes that experience algae blooms are said to be irreversibly fouled because too often, generic cleaning procedures do not fully remove the foulant, leaving behind a food source that allows bacteria to continue to grow. As access to clean water drives the need for seawater desalination, the need for targeted cleaning solutions will become an integral part of the process. This is just one example of Avista's targeted approach for hazardous algae blooms, which helps to reduce cleaning frequency, minimize membrane replacement cost, and extend membrane life.